Welcome, class. So now that we have a good understanding of how to quantify the amount of element or compound using our concept of a mole and molar mass, now we want to turn our attention to working a little bit more closely with understanding what a chemical formula represents. So, very much like the mass on the periodic table, it represents a couple of different things, right? So, that chemical formula can represent a single molecule of a compound, and it can tell me how many individual atoms are in that single molecule. So every molecule of CO2 contains one carbon atom and two oxygen atoms. But now with our understanding of the concept of a mole, right? If I have 1 mole of CO2 atoms, right? So of course, that means we're going to have one that's going to contain 1 mole of carbon atoms, so that if I take that whole group of 1 mole of CO2 molecules, so 6.022 times 10 to the 23rd CO2 molecules, right? If I count up all the carbon atoms, right, it's going to be 1 mole of carbon atoms, right? Because there's 1 carbon atom in every molecule. And of course, that means I would have 2 moles of oxygen atoms. So that formula can also represent how many moles of the individual atoms are in every mole of compound. And that's really the definitions that we're going to use, because again, we don't deal with single atom, we don't deal with single molecules, right? We deal with large numbers of them. So, we can answer the question, how many moles of oxygen are in 12 moles of CO2? Well, if we think about it, if I have 12 moles of CO2, and I know that if I look at the formula, every mole of CO2 will contain 2 moles of oxygen atoms. So every 1 mole of CO2 contains 2 moles of oxygen. My moles of CO2 cancel, and if I do my math, I end up with 24 moles of oxygen atoms are in 12 moles of CO2. So, big idea here. The subscripts tell us how many moles of the individual atoms are in a mole of compounds, and so we could use that to figure out how many moles of a particular element are in any number of moles of that compound. Now, we could also use it in terms of sort of a mass idea, right? Because if we combine this with the idea of molar mass that we just talked with, we can go from looking at how many grams of an individual element are in a certain mass of that compound, right? Now, the key here is the formula is based on moles, so we have to go through moles in order to get to our answer. So the idea is, if I know that I have 15 grams of NaCl, well, I can figure out how many moles of NaCl that is, right? So if I do the molar mass, right, the molar mass of NaCl equals 1 times the mass of sodium, 22.99 grams, plus 1 times the mass of chlorine, 35.45 grams, per mole. And so if I do all that, I get 58.44 grams per mole. And so, if I know that every mole of sodium chloride, 1 mole of sodium chloride, 58.44 grams of sodium chloride. My grams of sodium chloride cancel out. And if I were to solve this, I would get moles of sodium chloride. Now, based on the formula, I know that every 1 mole of sodium chloride contains 1 mole of sodium. So by doing this conversion, I switch my units now. So my moles of sodium chloride cancel, and I'm left with moles of sodium. So if I were to stop here, I would tell me how many moles of sodium were in that 15 grams of sodium chloride. Now, I want to know how much mass that represents. So again, now I need to use the molar mass of a sodium to figure out that every 1 mole of sodium weighs 22.99 grams of sodium. And so if I go through and solve out, cancel my moles of sodium, I get 5.9 grams of sodium are contained within that 15 grams of sodium chloride, keeping my 2 significant figures based on the original number in my problem. So if we take these ideas of the formulas, chemical formulas being based on moles of each element within that formula, and we combine it with something we talked about a little bit earlier, and that is this idea of constant composition, we can formalize this idea in something called the mass percent composition of compounds, right? Where we can express the percentage by mass of each element in a compound, understanding that this will be constant for any given compound because it'll always have the same formula, right? It'll always have the same number of each atom. And so we can develop these percentages by mass of a given compound. So the way this breaks down is that the mass percent of an element in a compound is going to be the mass of that element in 1 mole of compound. So in other words, how much of the molar mass is coming from that particular element divided by the mass of 1 mole of compound, or in other words, the molar mass, times 100 to put it as a percentage. So if I have any formula here, so let's say I have this formula, CCl2F2, and I want to know what the mass percent of chlorine is in that. So I want to know how much, what percentage of the mass of that compound is coming from chlorine. Well, I'm simply going to take the mass of the element in 1 mole of that compound. So in this case, the molar mass of this compound, right, is going to be 1 times 12 grams per mole, right, for the carbon, plus 2 times 35.45 grams for the chlorine, plus 2 times 19 grams per mole for the fluorine. And if I add all that up, I get 120.91 grams per mole for the molar mass. Now, this representing the part of that from each element. So, the carbon represents 12.01 grams, right? The chlorine represents 70.9 grams, and the fluorine represents 38 grams of that total. And so if I want to figure out the percent of a particular element within that compound, I'm simply going to take the percent of chlorine in this case, right, is going to equal the mass coming from the chlorine, which is 70.9 grams, divided by the tidal molar mass, the 120.91 grams, and these are of course grams per mole, times 100 to put it in terms of a percentage. So if I do that, I get that the chlorine represents 58.64% chlorine in this compound. Or 58.64% of the mass is coming from chlorine. And of course, because of constant composition, right, any sample of this compound is going to be 58.64% chlorine, right? So once we know the mass percent of a given compound, we can use that mass percent to tell us things, right? We can use that mass percent to, for example, allow us to answer the next question pretty simply, right? If you consume 22 grams of sodium chloride, and sodium chloride represents 39% sodium by mass, how much sodium have I consumed? So now I can take that 22.0 grams of NaCl and I can multiply it by the percentage of sodium. So now when we do this, right, we're going to multiply it by the fraction, or we're going to take the percentage divided by 100. So we're going to multiply this by 0.390 as the percent sodium. And if I do that, I get 8.58 grams of sodium. So that 22.0 grams of sodium chloride is 0.390% sodium, or 39% sodium, excuse me. And so 8.58 grams of that 22 are coming from the sodium. So now, being armed with this, we could go back and look at the problem on the previous slide where we had 15 grams of sodium chloride, and we went through the steps to figure out the mass of sodium by using our ratios. We could simply now multiply it by the percentage, the mass percent of sodium, and we would get the same 5.9 grams of sodium. So if we know the mass percent, or we can calculate the mass percent, we can easily then figure out how much of a particular element is represented by a particular amount of the compound. Now, in this particular problem, I only figured out the mass percent of one of the elements in a compound, but of course, you could then go through and use the 12 grams here and the 38 grams here and get the percentage of carbon and the percentage of fluorine. And of course, all those percentages of a given compound should always add up to 100% or very close to 100%. They may differ a little bit based on rounding.